everyone, we're Team 20, and this is our video demo for implementing Whack-A-Mole on the FPGA. So in this video, we'll start with explaining how our code functions and incorporating the main game logic. Then, we'll dive into demonstrating the main features of our game. And then lastly, we'll end with an explanation of our converted MATLAB script. And this part is just meant to show our thought process on loading sprites into the VGA module, should we have a chance to develop the game further. And basically, this slide is just meant to acknowledge the team members who implemented each game feature.
This is the simple implementation of the Whack-A-Mole game in Verilog. We have a more advanced version, but first I think it's easier to look at how the core game works in this file here. So as input, we have a universal clock, a universal reset, an input button for hitting the mole. Then for output, we have the mole itself when it appears, your score, the lives, and the state. We implemented the game as a finite state machine. So our three states in the simple version are the idle state when you load into the game, the gameplay state where you can actually hit the moles, and the end screen state where you go once you lose. Next, over here, we have a button tracking block. So the button only registers once you click it once. So you can't just hold the button to register multiple clicks. So now we have the main gameplay logic. First up is the reset logic. So all the local variables are reset upon that button click, and you get set into the idle state. Once you're in the idle state, you're pretty much just waiting for the next button click. This sends you into the gameplay state, and it sets your score to 0, your lives to 3, and initializes your mole timer and hammer timer. The mole timer and the hammer timers are integers that we pick to correspond with our current clock speed that correspond to 1 second and 3 seconds, respectively. We'll explain how they're used in a second. So, once you're in the gameplay state, the game first checks if you have 0 lives, and if you do, you get sent to the end state. If you don't have 0 lives, then the game first checks if your mole timer is 0. If it's not equal to 0, then it just decreases the mole timer by 1 and does that on loop. If it is equal to 0, then it sets the mole variable to 1, and the next conditional statement will be triggered on the next clock cycle. All this means is that you need to wait the duration of the mole timer between consecutive Whack-A-Mole events. Continuing on, we now have the hammer timer section of the code. The conditional statements implement the following logic. First, your hammer timer is decreased by 1, and the game checks if you've pressed the button yet. If you have, your score goes up by 1, the mole is turned off, and you reset the mole timer and hammer timer for the next cycle. If you haven't, the game then checks if the hammer timer has gone to 0. If it has, then that means you miss your opportunity window, and you should lose a life. It then checks if you've lost 3 lives, and if you have, sends you to the end screen state. Finally, in this version of the end screen, your score is set to 0, and it just waits for the button press to send you back to the idle state, where the game loop restarts. Now, we're looking at the advanced Whack-A-Mole module. The first thing you can note is the added button inputs, random number inputs, and mole outputs. This allows us to have different moles appear and requires you to press different distinct buttons to hit each corresponding mole. Additionally, the random number input allows us to have variability in the order and variety of the moles that appear at what time. As of the time of this recording, the randomness code is commented out since the connection between the random number generator module and the gameplay module has yet to been written. However, as you'll be able to see down below, we were able to use the urandom function, which is used just for simulations and cannot be synthesized to the board, to show on the test bench that the random logic should work out fine. Moving right along, we can also see a couple newly added variables, such as the windscreen state, a couple added mole timers, a couple added button previews, some blink counters, and the reduced speed and high score variables. In our button tracking loop, we can see that the different button previews allow us to detect different button inputs. Later on, we can connect this up with the accelerometer code in the top module to get an alternative mode of input. In our main game logic, we have the added reset for the new mole timers and button previews, but we also have the reset of the blink counters. The blink counters were added to provide more variety and fun in the end screen state. It's pretty much just used to have the moles dance in a choreographed pattern, which should be nice visually. You can also now press any of the buttons to escape from the idle state and enter the gameplay state. In the gameplay state, after checking if you have 0 lives, it then checks if you've reached the max score, which we've set to 64, and if you do, it sends you to the windscreen state. We also have some revamped logic to accommodate the multiple mole timers. So, due to the randomness, it just detects which timer goes off first, and once that timer goes off, it sets the other mole timers to 0 and allows you to proceed to the next bit of code. The revamped hammer timer logic now checks if any of the moles have been turned on, and then checks the 2 cases. The first, which is you've hit the correct mole with the correct button, or you use the wrong button, or you let the timer run out. Both of the negative cases just does the standard decrease life logic. The last bit of newly added code here is the dynamic hammer timer decrease. So essentially, once you've hit certain score milestones, the hammer timer will get shorter, and it will make the game more difficult. Right now, the difficulty increase is pretty small, but we can manually go back and change just the reduced speed variable to make it much more difficult. This also provides opportunities for code extensions to provide more challenging and difficult modes. Lastly, we have the windscreen state. Currently, it's written in the binary because at the time of this recording, Vivado was acting up, but we could just write the windscreen state instead. First, we have the actual dancing mole logic as alluded to above. All this does is just blink the moles according to this predefined pattern, and you can mix this up to your heart's content. In response to some of the feedback from our presentation, it was mentioned to maybe try to add a multiplayer mode. Given that the final version of the game implies tilting the FPGA to the correct mole, it didn't really make sense to add multiple players to input at the same time. So we came up with the idea to add a high score feature. Essentially, it just checks if you've beaten the previous high score, and if you have, replaces the high score with your score and displays your score on the screen, and if you haven't, just displays the high score. This is also another opportunity for code extension, since we can have multiple high score variables defined above, add them to the output, and then have a list of high scores like an arcade machine. Lastly is the windscreen. Currently, the only way to leave it is by resetting, which makes sense since you probably don't want to compete anymore once someone actually beats the game. But it's also left open for more code extension opportunities if you want to display something in the end screen.
Hi everyone, I'm Arielle. I wrote the modules for incorporating the game's VGA display. So for the demo, I will be showing two examples of the VGA display in action by showing the display during the gameplay state and during the end screen state. So what you see now is the gameplay state, and at the time of the recording, we only implemented the game to be playable with one mole. So this is just the game playing with one mole. And here is the end screen state, which basically displays the dancing mole logic that Jacob explained. This just displays the mole's appearance according to a predefined pattern, confirming that on a basic level, the VGA modules were successfully implemented. So one of our interesting features is having the user input register via the accelerometer. This basically allows the player to simulate a physical whacking motion. So in this clip, I essentially try to hit the mole when I see it appear on the screen, and successfully doing so will cause the score to increment.
Going back to our slides from the presentation, we did use some source code that allowed us to utilize the serial physical interface in order to communicate with the accelerometer. The source code allowed us to get some accelerometer values, which I found a pattern in, and allowed us to map those to tilts, which we used instead of buttons for our whack-a-mole cam. So essentially, what would happen is that when you tilt a certain thing around its axis, around y or x axis, only one of those values will be changed. So we use a pattern with the values, the fact that only one value changes at a certain axis, and we also looked at the sign and the values, that how the values change within that domain. So for the y-axis, we found that this tilt, we found a certain amount of tilt that we wanted, which was like 5 to 8, quote unquote, just the values of tilt that we wanted. That would correspond to a left tilt, and then on this side, it would be a negative value from 11 to 7. And then for the x-axis, which rotated this way, and the y-axis was this way. So x-axis is this way. We found that this way was a negative value corresponding to 10 to 7, and this way was 5 to 8, with a positive value that corresponded to the bottom. So using these signs and the values and the fact that only one of these two values, x and y, were changed, we were able to relate those to the tilts that we wanted. So left tilt, right tilt, front tilt, and back tilt.
Hi, I'm Kofi, and I worked on the gameplay segment of the code, and more specifically, the random number generator. The random number generator specifically allows for multiple modes to appear at once and appear randomly, so it's an interesting, engaging game. So the way I implemented it was through a LFSR that had a seed that was reused throughout the program so things stay consistent.
With the RNG feature implemented, we now have a full demo of the game, and we're able to show all 4 tilts on the accelerometer. Each box on the screen corresponds to a specific mole, and to increase your score, your tilt direction must correspond to the mole that appears on the screen. So for example, tilting the accelerometer to the right will whack mole 4, and the player must tilt the accelerometer to the right when the bottom left mole appears.
In order for us to load the JPEG file into the FG board, we need to have a MATLAB code that converts the JPEG file to MEM file so that it can be read in the ROM. Because JPEG file is a compressed form and cannot be read by the FPGA directly, so we need a converter. So this is a code which map out the color and extract it into RGB and make it into a MEM file corresponding to the specific pixel. And we have a back to JPEG converter which can help us verify whether it is correct.